So let's suppose we have some position is some function of time, and it's s of t. And you're going to be given the position function, but I realize one of the things that we've been doing is giving you the graph of the position function, and I'm going to give you some information about s of t through the derivatives. So let's suppose we follow our rules: power rule, quotient rule, product rule, and we find the s prime of t, and we say that this is the velocity. And in a lot of ways this makes sense, because when we take the derivative with respect to time, we're finding the change in position with respect to time. So this sounds like a velocity, right? Maybe this is meters per second. So what we do is we take the s prime of t and we set it equal to 0, and we find the positions where the times when we find the roots of this s prime of t equation. The roots are just when it's equal to 0. So let's suppose, just for the example, we find that at t equals, let's say at t equals 5, and at t equals 6, we find that the s prime of t is equal to 0. So what does that mean? That just means that the velocity at time equals 5 and time equals 6 is equal to 0. Also, we know that the derivative is the slope of the tangent line. So let me just, I'm going to put an coordinate plane here, and this is going to be t, and this is going to be our position function. I'm going to graph our position. And let's look at this is another t-axis. So we know at t5 and t6 we have these 0 slopes. So I'm just going to graph. Let me just say, I'm not going to graph them, but we just know that this is where the 0 slopes are at 5 and 6, and we're going to remind ourselves of what that means. So and then we want to know where we know that the first derivative is 0 here, and let's suppose we find that the derivative is positive to the left of 5, then it's negative from 5 to 6, and then it's positive. So what does this mean? That means our graph has got to be upward sloping from 0 to 5, and then at 5 the slope of the tangent line is 0. So our graph could easily look like this. It doesn't have to look like this. It could be lower, it could be less steeped, but we have a 0 tangent here, so it definitely turns around, and then it definitely goes down. Here we have a negative slope, so all these slopes in here that are tangent to this line are downward sloping, and then it comes back down to a 0 slope, right? Because this corresponds to 6, and then it goes back up again because we know it's positive right here. And so where is the so let's talk about acceleration. So this is just talking about velocity sign. I want to talk about acceleration. If we were to find the acceleration, we would find that in acceleration, again, this is going to be the second derivative. The acceleration might have a magnitude, but we can say what the sign is. Somewhere in here, there's going to be a point where acceleration is equal to 0. And because just imagine, right? Remember when we throw a ball and it goes up and down. This has a negative acceleration. It's accelerating towards the ground. And this let me do that in red. This has an acceleration less than 0, or negative acceleration. And so over here, because you can see this graph looks a lot like that, it's opening down, acceleration is going to be negative over here and positive to the left of some point. I don't know what that point is, but this is some point between 5 and 6. These are things that we'd see if we took the derivative, and remember this is s double prime of t, and this is s prime of t. So the graph doesn't have to look like this. I realized we were showing you a lot of the graphs, but if we knew this information, if we knew these zeros of our derivative were at 5 and 6, and we knew that we looked at our derivative and we found these signs, we would be able to intuit some kind of graph like this. Okay, so what's the next part? So we want to know, let's talk about the distance the particle traveled. And let's say it's from 4. Let's say it's from 4 to 7. Deliberately took the interval outside of there. So we're going from this position to this position. Well, the net position, or the displacement, would just be from S of 4 to S of 7. But I didn't ask that. I asked, what's the distance it traveled? Well, when it traveled from 4 to 5, it went from here to here. Okay, and I mean, when I say it went from here to here, this is the position. So really, it went this far, right? Because this is the position of the particle, right? I hope that's clear. It did not travel along this curve. This is the position as a function of time. It traveled from S of 4 to S of 5, and that's the this is 5 right here. So that blue, the blue part, that distance, well, displacement, is S of 5 minus S of 4. And then it turned around, right? The velocity is 0. It turned around and started going backwards. Here it looks like it's going downwards, but it's really, it has a negative velocity. It's really going backwards, because, I mean, backwards is relative to this scale here. So what about that part? Well, it started here and it went all the way down to this other point where it turned around. So let's say it's right here. So it went, and I'm trying to put it up here, it went this distance. Okay, it went S of 5. I should put S of, here's S of 5 over here. S of 5. It traveled from S of 5 to S of 6. So that green distance is S of 6. The distance is equal to, I should put absolute value, because this could be negative. Let's do absolute value of S of 6, right, with the other turnaround point, which is right there, to S of 5 minus S of 5. And then it turned around again, which we could figure out from these from our derivatives. It turned around again, and how far did it go? It went from S of 6. What are we going to use? Orange. It went from S of 6 to S of 7. So that's this part, S of 6, all the way up to S of 7. So that's what I asked for. The distance. So the distance. Let me do that in yellow because we're going to be consistent. Or about blue. The question was, what's the distance it traveled? Not its displacement. The distance traveled is equal to, it's going to be this plus our orange part. The distance of our orange part is S of 7 minus S of 6. And you can kind of see where these match up, right? Since these are the turnaround points, I'm going to circle those in blue. These are turnaround points. It's going to be first turnaround point from the beginning to the first turnaround point, this turnaround point to the other turnaround point, and then the ending, which is right here, to the second to last, last turnaround point. And we get these points, we get 5 and 6, for example, we get those from analyzing the derivative. We got 4 and 7 because I asked for the distance traveled from 4 to 7. Oops, the distance traveled from 4 to 7. So that's how we got those points. And we got the fact that they were turnaround points. We got 5 and 6 as turnaround points from the information we got from the derivative. I hope that was helpful.